Alright, let's begin with a word of prayer. Dear Lord, thank you for this day. Please bless my teaching today as I try to cover this chapter. Amen.
Amen.
So on that note, essentially...
you have at least 2 days, so...
Right, well, so like what I'm going to try to do today, there's a lot of technical material in this chapter, and it's very long. So instead of aiming for 2 days for a lecture, I think I'm going to try aiming for 1, and then maybe it'll spill over into 2. So really, I'm just going to try to do like a very brief overview over this, but I'm going to try to touch every topic. So first off, definition of a natural transformation. If you have C and A, which are categories, and you have 2 functors from C to A, covariant of course, we say a natural transformation tau from F to G is 1 parameter family of morphisms, so 1 for each object in the category, such that the following diagram commutes. So essentially, what I found in my experience with category theory is a really useful way of thinking about functors often is as a construction in the codomain of the function. So what a natural transformation is basically a natural way for moving from one categorical construction to another. So you just have these maps here and everything commutes. So another definition we say that natural transformation tau from F to G is a natural equivalence if every tau sub C is an equivalence, aka isomorphism. So that's a pretty natural definition, pun intended. So they have some examples here. I'm not going to read them out, but the first one, example 9.1, I found pretty interesting. If star is a 1-point space, say star is equal to singleton A, our function h from star to x is completely determined by its only value, x equals h of A. In x...
What page are you
on? 229.
Okay.
So we denote h by h of x. So h of x, or let's call it h of A of x, is just the constant function A, for example. So, oftentimes, we make this identification here between the constant function A and A itself. And it turns out that this identification, viewing this as the Hom set from star to x, you can actually make a natural identification here by defining tau of x is equal to, I guess this is big X, h sub x. And they show here that indeed the relevant diagram commutes, and thus this is a natural transformation. They say you can also prove it's a natural equivalence. So the next example here I also think is interesting. So you can view the identity functor on the category of abelian groups as isomorphic to Hom, from Z to blank.
Right.
And so they say this is essentially a formal way of representing the fact that any homomorphism is determined from its value, or any homomorphism with domain of Z is determined by its value on 1.
Yeah, you hear a lot of people just say that abelian groups are Z homomorphisms. Yeah.
And then finally, this last example, I think we covered in linear algebra.
It's just what's natural.
It's the fact that, V double dual is, I don't think they have a notation for this, so I'm just going to say.
By the way, I think it's some of the absolute
Yes.
coolest language in all of linear algebra.
Double dual?
Yeah, like
Dual.
the dual, double dual
Yeah.
space. Although the annihilator is, I love saying, when I get to talk about the annihilator, I just feel like it's got an intrinsic. Although the musical morphisms are pretty fun. I probably shouldn't be talking about those in linear.
Yeah.
Much less here.
True. All right,
Don't agree with that. You of all people should be all for musical morphisms.
All right, so those are natural transformations. So basically in this chapter, we're going to go over a few different examples of them in algebraic topology. So the very first one is the Eilenberg. Make sure I spelled this right.
It's funny how ugly the dual, double dual stuff gets when you go to functional analysis.
Axioms.
You guys will see that soon enough.
So, I don't understand the significance of this first definition here. I wish they would have given a more thorough exposition of it, but definition, pair x comma a of spaces, let's say x comma a, where a is a subspace of x, so essentially something in top squared. Is called compact polyhedral pair. If there is a simplicial complex K, finite of course, but I think I mentioned earlier that everything in this book is finite, so.
Shouldn't feel that way.
And a subcomplex, L of K. This is the part to me that I don't understand why that's needed, but that's how they define it. And homeomorphism F from the underlying space on K to X with F, or the image of the underlying space on L, equal to A. So kind of if you want to draw a picture of this, let's see, you've got some simplicial complex K, this whole thing, and then you got maybe L subcomplex, then you've got this homeomorphism here, F into some other space where, draw this curved or something, I don't know.
Whoa.
This then is A. So I don't know why you can't just skip the fact that this is a subcomplex and just have complex. I don't know why the structure of this simplicial complex L is sitting in is needed, but apparently it is, so I'm not going to argue with them. But so, what we use this definition for, definition, let script, oh that's not a C. I don't know what I was doing there. Let me try this again. Script and C. Good enough. The category of compact polyhedral pairs which they do not define, but I assume, what are the morphisms here? What would the morphisms be? I guess it'd be a morphism in top squared that also preserves this homeomorphism somehow, I guess. They don't really give the details of that unless I'm missing something. But with that, we define a homology theory. H partial on that category. Doing it again. Is a sequence. I'm just going to do C. For n greater than or equal to 0, and a sequence of natural transformations Hn to h of n minus 1 of R, where this thing here, they say is from exercise 94, and it's a functor from, right here, x comma a, just a. So again, I'm not really sure what the intuition behind that is, but without loss of generality here, if you were just considering this to be the empty set, we could just consider normal topological spaces here instead of dealing with subspace nonsense. So don't worry about that too much. Such that following axioms hold. And we've covered all of these, so I'm not going to write them down.
Save them, man.
But homotopy axiom. If two functions are homotopic, then they induce the same homotopy group, essentially. Exactness axiom, for every pair of inclusions, blah, there is an exact sequence, blah. Excision axiom, for every pair xa and every open subset u of x with the closure of u subset of the interior of A, the inclusion x minus u, comma a minus u to x comma a induces isomorphisms from hn of x minus u, comma a minus u to hn of x comma a. And finally, the dimension axiom. If x is one point space, then hn of x comma empty set is equal to 0 for all n greater than 0. And importantly, they call, let's write this as another definition, h0 of x is the coefficient group. So for example, in everything we've seen up to this point, this is equal to what?
Z.
Right. Exactly.
Yeah.
So we'll see later in this chapter homology theories with other coefficient groups. But every
Universal coefficients theorem.
Yes, exactly. I will be going over that very briefly.
One of those things.
Because actually proving it is
one of those
complex.
things I actually understood when I took my algebraic topology qualifier back in the day.
So all that to say, theorem,
I think I knew more then.
which they don't even prove here. This is the Eilenberg-Steenrod theorem. Any two homology theories with isomorphic coefficient groups on the category on script fancy C are isomorphic. So, Oh, I don't think I actually gave the definition. Isomorphism of homology theories is a sequence of natural equivalences making this diagram.
Oh,
for you.
yeah. Right.
I mean, you guys can see it in your book.
Yeah, we can.
Right. That thing. Yeah, so they didn't even prove this here, so I'm not going to. I assume, given the proofs in this book, it must be like at least 20 pages long. Maybe not, but anyway, so for example, the coefficient group for singular homology and simplicial homology is Z. So this theorem tells us that as homology theories, those are isomorphic, and they remark here that means not only, as we've proven, are homology groups the same, the induced homomorphisms are also essentially the same. And I think we've seen some lemmas to that effect, but this result
Right.
now with the natural transformations formalizes that all in one big theorem.
It's like we have the singular calculation, we've got the simplicial calculation, there's another one, the cellular homology, which we didn't cover.
They say cubical homology
And
a
and like
bunch of homology theories.
what these Eilenberg-Steenrod axioms are saying is like it doesn't, if you come up with some other scheme to calculate the topology, it's the same stupid thing.
Right.
It's very cool. Like this result is just amazing, I think. I don't know. But
So I also think interesting here on page 232, they talk about suspensions of the space. How actually
an
this
extra,
this dimension axiom, right?
uh-huh.
From that you can actually construct the homology of spheres, right? Because you start out with a point, you take the suspension of that, and you keep doing that, and that gives you higher and higher spheres essentially.
Blowing bubbles.
So, you know, all the work we did before. Calculate the homology of spheres. You could have just started from this axiomatic standpoint.
Oh man.
And yeah, because essentially they say on page 233 here, the relation you can find is that...
This is good to know, Nathan. Next time the Calculus 3 class asks me what the homology of spheres are, I'll be like, well,
Someone asked you?
You start with the Eilenberg-Steenrod axioms. And then you look at the suspension of a one-point space.
Yeah.
Sorry.
So,
Sorry.
this here is essentially the relation you can deduce from the axioms, apparently. So let's see.
An extraordinary cohomology theory.
Yeah, I thought that was interesting too. I don't know why it's called a cohomology theory if it's
It's almost a homology.
almost a homology theory. I think that was kind of weird, but...
Yeah.
Alright, so I'm going to erase some stuff because this was one of the shorter sections. So I'm looking for space. I think I can erase this probably. Natural transformations are, again, pretty natural, so should be ingrained in your mind by this point.
So you can also replace the excision axiom by an exact Mayer-Vietoris sequence, he says. Interesting point.
Alright. So, let's see how I want to do this next section here. These next two sections are kind of related. So, the section here, chain equivalences, there's a lot of algebraic lemmas and things. Let's write it down.
So what's the big idea of this section?
So essentially here, and they pretty much say it, beginning of the paragraph, the main theorem in this section is a necessary and sufficient condition that chain map between free chain complexes get chain equivalence. And I think we're going to use that in the next section. So,
Chain complex is free if each of its terms is a free abelian group.
right, so that's pretty natural definition. Let's see here. I think I'm basically just going to go over some of the main theorems of the section. I know a lot of the algebraic lemmas are pretty interesting, like corollary 9.2 here. They have a lot of interesting things you can deduce when you have morphisms between free abelian groups. But that's not really important to the overall idea here, so I think I'm going to go over that. One of the big theorems they use here, though, theorem 9.3, is that every subgroup of free abelian group is free.
Free indeed.
So they have pretty interesting proof here. They basically use induction to split up the structure of the free abelian group, but that's kind of involved, so I'm not going to go over it. Then the next theorem they have here.
No, that's what I call linear algebra.
9.4. A free chain complex, which I didn't write down what we said earlier, is just a chain complex in which each term of the chain complex is a free abelian group.
I wonder if somebody's done Freebird but with free chain complexes.
It is acyclic. So remember, that means all the homology groups are 0. If and only if it has a contracting copy. So again, going through this entire book, there's just so much deja vu, like you're doing the same thing but in different contexts. I wonder if in other books, like he says here, he doesn't develop the category theory until it's needed. I wonder if in other places they're just like abstract nonsense from the beginning, like first 100 pages, and then boom, you have everything.
Well, that is Rodman's way of teaching is he develops as he goes, as opposed to the more logically raw and efficient thing of just doing unjustified nonsense at the start and then going, by formal nonsense we've already done, true,
Right.
He's trying to build an intuition for where the formal nonsense came from. But
so this is very similar to
blessing
what
and
we
curse.
proved for other homology theories and stuff. We're just doing it now for chain complexes, specifically free chain complexes.
Mm.
So the next thing I get into, they have something called the mapping cone. So they define it. I guess I should go into that. Yeah. So this I don't really understand the intuition for, but I guess it's some way of the idea here is they're representing a chain map as a space, I guess. And then they're using that to actually prove these theorems. So if you have a chain map, then they define the mapping cone CF, which is chain complex. Yeah, so that's a bizarre thing to me. They call this the mapping cone, but it's a chain complex. So it seems like weird terminology to me. But they say whose nth term is lost my place here. A sub n minus 1 direct sum B sub n, and whose differentiation operator, I'll just give it matrix form because that's easier to write, is negative partial 0 f partial prime. So I'll just read these next few lemmas here. Lemma 9.5, if f from A star to B star is a chain map between free chain complexes, and C of f is a free chain complex. Theorem 9.6, let f from A star to B star be a chain map between free chain complexes. If C of f is acyclic, then f is a chain equivalence. Lemma 9.7, if f from A star to B star is a chain map, then there is an exact sequence hn plus 1 of cf to hn of A star to hn of B star to hn of cf, etc. And so finally here we get to theorem 9.8, which is the big theorem of the section. So A star, B star, free chain complexes. And let f be a chain map. Then f is a chain equivalence if and only if the I guess nth term of the induced map is isomorphism for all n. So that is essentially what we said at the beginning, that hang on a second. Necessary and sufficient condition that a chain map between free chain complexes be a chain equivalence. So that's what we have. So that's all kind of technical, and what we use that for is this next section here, acyclic models. And so this is also kind of technical, but it's the goal here I think is a bit more concrete. Acyclic models is a technique of constructing chain maps and chain homotopies. So specifically, later we'll see the major theorem in this section is that from a natural transformation, actually you can induce, well, natural equivalence, you can induce a chain equivalence, which is interesting. So, theorem 9.9. Consider the commutative diagram of abelian groups. So you got T, S, C, R, B, P. A So bottom row is exact. And ST equal to 0. Then, got the dashed lines there. There exists a homomorphism C that makes the first square commute. So I think essentially what they do here, this theorem 9.8, the necessary and sufficient condition we need for F to be a chain equivalence, this theorem lets us characterize it in terms of isomorphisms between homology groups. So essentially, I think what they're doing in this section is, this theorem 9.9 here is a theorem essentially at the level of, individual spaces and homology groups. And later in this section, we're going to kind of lift that using this theorem to the level of chain complexes themselves. And that's what we're going to use to get our main theorem. So then part 2, I'm not going to write out. This here we're going to see again later, which is why I wrote it out. But consider the diagram of abelian groups.
Page on, I'm sorry, I lost my...
238.
yeah.
Which the rows are chain complexes, each S of I is free abelian and the bottom row is exact. And there is a chain map T from F to E with Fe equal to epsilon T naught. Okay. So, next definition here. Category with models.
Coker, it reminds me of a job interview I had once.
What's that?
I had an on-campus interview at Coker College in South Carolina. In my interview, I mentioned that I thought undergraduates, good undergraduates, could possibly do undergraduate research in supermath. One of the faculty sitting in the audience laughed out loud. I was like, hey, that's not cool. So, it's just as well I didn't get to work there. It's very flat.
So category with models, essentially you have a category along with a subset of its objects.
Uh-huh.
What we're going to see later is that essentially, if you choose this subset appropriately, right?
This is a Trump category. Anyway, go on, yes.
A Trump category? Oh! Right, so if you choose these appropriately, you can essentially get this result at the level of chain homotopies and chain complexes when you only prove them for the models. So essentially that's the usefulness of this. It's kind of like a basis for topological space, right? You choose a subset and it makes things easier to prove. So then this is kind of a 2-in-1 definition. So F is a functor from C to abelian groups. And then F model set. Oh, F model set. You shouldn't have made that Trump joke. Is an index set.
Oh no.
X equal X sub j element F M sub j such that j is element. So, oh, that's interesting. So I guess they're kind of assuming here implicitly that this is like a concrete category. so the objects are actually sets, because otherwise this definition doesn't really make sense. Right, but this M sub j is just an index of all the models, and this is an element of the functor applied to each of those.
And the definition, I think it says J is an element of capital J. Isn't that thing?
Right, that's an indexing set, though.
Right. You were at M, though.
Oh,
I'm sorry.
oh, yes, thank you. Yeah, that wouldn't make sense, would it? Okay. So then we have another definition. Let's see. The category with models. And let F from C to AB be functor. Then F is free with base in M if one FC is a free Euclidean group for all objects C, and 2 there is an F model set such that
It's 4 o'clock.
for all objects C, the set, yeah, I guess probably this will take me 2 lectures. I'm glad I planned for one. X sub j x and sigma sub j to c basis of FC. So essentially, it's kind of what it sounds like. You have models appropriately chosen so that for each of these FC, which is a free abelian group, you get a basis by applying your functor to the F model set. All right, so from that, some more room again. Erase just this. And we get lemma 9, 11. Let's see. Category with models. M. Consider unit diagram of functors and natural equivalences. Right, so this hasn't been done before, but much like you can have these commuting diagrams of objects and morphisms, you can also have them of functors and natural transformations. You also can, of course, think about this as just a commuting diagram in, well, I guess it's not the category cat. I guess maybe it's the 2 category of cat, but I digress. Point is, as I think you'll see, this is essentially the version of theorem 9.9i, but with functors and natural transformations. Dashed gamma beta alpha rho pi, in which that's right, sigma of tau is equal to 0, and the image for rho is equal to kernel of pi, in other words, exact. Then there exists a natural transformation in gamma, making the first square commute. Where have we seen this before? Right, so that's sort of what I was talking about with taking what we know and lifting it up to a higher level. So, but what they say is, it is simplest to regard lemma 9.11 as merely a functor version of the elementary theorem 9.91, but lemma 9.11 is stronger than this. The biggest thing is that this only has to be checked on the models M in your model set. But they say the theorem we seek of this is a version in which the results in Abelian groups are placed with the results in comp. So this is where the stuff from the last section comes in handy, like I was saying. So, let's see. Give this definition. If E comp is a functor, then object C category is E acyclic if, shocker, Hn of EC equals 0 for all n greater than 0. Would not have expected that. So now we finally get into the main theorem of the section, which I think is pretty interesting. Acyclic models. So, let's see the category of models, or category with models. Then let F E from C to comp non-negative functors, which I forget where they define that, but basically it means that the image here in comp isn't indexed past 0, essentially. Let's see, I think they define that. They define that in the paragraph above. Of course, if E from C to comp is a functor, then Hn of EC is defined for every object. Moreover, if E is non-negative, that is E sub I equals 0 for I less than 0. So that's what they mean by that. Alright, so then for each k greater than or equal to 0, assume that f sub k is free abelian with base in m sub k subset of m, and that each model m in m is E acyclic then 1 for each natural transformation phi from h naught of f to h naught of e, there's some natural chain map tau f to e over phi. That is, there's a commutative diagram. Let's see, f1, f naught, h naught of f, 0, e1, e naught, h naught of e, 0. Two, if tau and tau prime are natural chain maps over phi, then tau and tau prime are naturally chain. On topic. Finally, this last part, which I may be incorrect, but I think this is the most important part of this theorem. Assume that E sub k is free with base m sub k contained in M, and that each model M in fancy M is F acyclic. Then if phi is a natural equivalence, then every natural chain map tau from F to E over phi is a natural equivalence. So essentially, given a natural equivalence phi, right? These natural chain maps tau we can convert into natural equivalences, which I thought was pretty neat. So the last part of the section, talk a bit about augmentations, which are kind of a formalization of what we did with the reduced homology earlier. Then they talk about something called acyclic carriers, which they call a cheap variant of acyclic models. So I'm not going to talk about those if they're just a cheap variant.
Yeah. Fair enough.
They're trying to think of something Trump would say. What would Trump say about acyclic acyclic carriers?
Losers.
Yeah. Wrong.
They wanted to join the F model category. They asked me many times. Oh, but now they're criticizing me. Oh, sorry, I've gotten too far into my Trump.
Alright, so this is actually, this section's probably my favorite part of this chapter. Kind of get into some of the applications here.
Mm-hmm.
And prove the Lefschetz fixed point theorem. Proof of that's kind of interesting. Again, I don't think I'm going to have time to go through it. I don't know, maybe now that I'm stretching this over 2 weeks, we might get into it next week.
2
But,
weeks. You mean 2
or
days?
2 days, yeah. Yeah, not 2 weeks.
Yeah.
We want to talk about cohomology.
Yeah. So. That reminds me, Daniel, I'm next, right? Is that right?
Yeah, you're talking about cohomology, I think, right?
I think that the chapter that I was supposed to talk about, we're skipping over.
Okay.
So how much time do I have?
Yeah, 20 minutes.
Alright, so I guess
25.
I'll probably...
25 minutes, actually. Yeah.
Well, I might even be able to finish this section. Then I can just talk about tensor products on Thursday.
So Daniel, you didn't want to talk about like the anything in the homotopy. Were you going to talk about the homotopy? Can't remember.
Yeah, the homotopy groups, I think.
That was what you were going to do.
Yeah.
So you're up next then. That's cool. Now we'll have to talk about the cohomology. Yeah, 3 days.
Alright. Actually, maybe I'll just go through this section and we can finish then.
Okay.
Because the last section, they basically just discuss how to calculate the homology of direct products. And they're able to express that using tensor products, essentially.
Okay.
So this section, I think, is a lot more interesting. And so we actually use some of the simplicial approximation stuff we did before here. So, first off, they say in singular theory, we saw that the, what does it stand for? Standard division? Simplicial division?
Subdivision.
Subdivision?
Subdivision.
Subdivision. Thank you. So we saw in singular homology that the map induced by subdivision actually gives us the identity. But the same is not true in simplicial theory. So our first lemma here actually is that map induced in simplicial theory is actually an isomorphism. Lemma 9.16. For every simplicial complex K, SD from C star of K to C star of SDK induces an isomorphism in reduced homology. So, next lemma here is even nicer. So I think, okay, so we got the same setup as before, except now we have phi is a simplicial approximation to the identity. then the map induced by phi is equal to subdivision maps inverse, which is an isomorphism between the subdivisions of K and the reduced homology group, or reduced homology group with subdivisions of K and reduced homology group of K, which is nice. So he says here on top of page 249, the purpose of these lemmas is to prove the Lefschetz fixed point theorem. So, bottom here they give this definition. If G is a finitely generated abelian group and you have homomorphism, of course if it's a free abelian group, we just define the trace naturally as you would in module theory. How they define it is the trace of the induced homomorphism on the free abelian group G mod the torsion group of G, which is of course free abelian. So that's a pretty natural definition.
So that's what this page is leading up to.
Right.
Yeah.
So now, this definition I think is pretty interesting. This is the Lefschetz number. So G naught, GM, the sequence of finitely generated abelian groups, and let H sequence of morphisms between them, where H sub I homomorphism, of course, the Lefschetz number of H denoted by lambda of H is the alternating sum A1 to the I of the trace of the individual homomorphisms. So, example. So I think this is really interesting. Of course, it kind of looks like the Euler-Poincare characteristic, but it's using traces.
Yeah.
So example 9.7 here. If you let F just be the identity on K, then the trace of map induced by F sub I is equal to the rank C sub I of K. So lambda of the identity on K actually is the Euler characteristic. So this is sort of a generalization of that.
Oh.
So they have a few lemmas here. Lemma 9.18, let C be a chain complex of the form 0 CM C0 to 0, which each C sub I is finitely generated, and let F from C to C be a chain map. Then the Lefschetz number is the same as the Lefschetz number of the induced homomorphism. So, without the theorem, 9.19, let X be a compact polyhedron, and let F from X to X be continuous.